In this video, I describe some possibilities for the human physiology projects you can design with your group. For the first half of the semester, you will be doing an independent project with your group, just looking at some aspect of human physiology. Generally, this comes in the form of answering the question, what is the effect of blank on blank? The first blank is something that might affect human physiology. And our projects tend to group into two different categories. Some projects tend to be the effect of something calming, like meditation or yoga or time in nature or something like that. And the other set of, and then other projects tend to group more into something stimulating, like exercise or caffeine, stressful situation, something scary, extreme temperature, or something like that. So what is the effect of one of these either calming or stimulating things on some aspect of human physiology? And then we measure some aspect of human physiology to see what the effect is. So some of the possible dependent variables, these are the things about human physiology that we're interested in seeing if they are being affected. We can measure in this class include heart rate or pulse, blood oxygen level. We can do an electrocardiogram. We can measure blood pressure, grip force, reaction time, and respiration rate. So those are some of the things we can measure. There may be some other options as well, but these are the ones that generally most people measure, and we have the equipment already to measure them. One of the devices we have for measuring heart rate is the pulse transducer that you used in Lab 1. So this can measure heart rate. It's actually also sometimes used as a trigger for reaction time experiments as well. But as you saw in Lab 1, it can record heart rate over a period of time. And then you can see how heart rate varies, how it changes, how very variable it is. So it records it over a longer time, or can record it over a longer time. An ECG is an electrocardiogram, and it records the electrical activity of the heart. So you put these little stickers on 3 different places on your body, and then there are these wire leads that come from the stickers that attach to the equipment, and it measures the electricity running through your body and going through your heart. This wave that you see here, shown here is an example of one wave of the electrocardiogram, or one beat of the heart. And it's not a single action potential, but it is the sum of all the action potentials, all the ups and downs, and everything is related to how the up and down on this recording is related to how the electrodes are placed on the body. The P wave represents the atrium in your heart depolarizing, so contracting. So you can see how fast it's happening, how big of a contraction it is using the electrocardiogram. The QRS complex represents the ventricle depolarization. The atrial repolarization is hidden in there, but the contraction of the ventricle is the main thing that's really represented by the QRS complex. The T wave is then the ventricle relaxing or repolarizing. You can also use this to measure heart rate when you measure the one R wave to another R wave. So the R to R is going to give you the heart rate if you measure a bunch of them, just like we did with the pulse transducer. The PR interval gives the time of atrial depolarization. The QT interval gives the time of ventricular depolarization and repolarization. The R wave amplitude tells you how many myofibers are depolarizing and is correlated with contraction force. And increasing venous return should increase the R wave amplitude. If you're interested in looking at different aspects of the electrical functioning of the heart, then you should read more about ECG recordings and what they can tell you, and decide if there's something important about the ECG recording that would be of interest to you. We can also measure heart rate or pulse using a finger pulse oximeter that we have a few of. This just slips on your finger and it will give you the percent saturation of oxygen that your blood has, so how much oxygen is being carried around by your blood, at least in your fingertip, and it will also give your pulse or your heart rate. Strangely enough here, the oxygen saturation is 97% and the heart rate is 97%. So they are both the same, but they are not always. This device is really easy to use. One downside of it, though, is that it doesn't record anything. So you would have to write down these numbers anytime you want it recorded, and you can't get a long recording where you get the variability or an average or something like that. You just have to write down what it says. But an advantage is that you could go outside of the lab room and use this device, so you wouldn't have to stay in the lab room using the device, whereas the other two that I just talked about are attached to the power lab that we used in the first lab and have to be used in the lab room. So just to reiterate, because a lot of people like to measure heart rate as a useful indicator of what's happening with your human, physiology. So we have a bunch of different options here for measuring heart rate. You can use the pulse transducer, the finger pulse oximeter, or ECG. Some pros and cons are listed here. So the pulse transducer, there are none of those electrode stickers. So you're not using any consumable thing that you have to throw away. So it's cheaper. Sometimes the electrodes have to be placed on a leg or something. And so sometimes you have to take off socks or tights or something. So with the pulse transducer, you don't have to do any of that. Some cons to the pulse transducer is it's very sensitive and noise can be a problem. As maybe you saw in lab 1, just moving a little bit or laughing or something like that will really affect it. The finger pulse oximeter is totally wireless, which is a pro. You can go elsewhere to measure it. It measures oxygen saturation of the blood, so could be a useful measure. But it doesn't record the pulse. So again, you would have to actually write down the numbers, and you wouldn't have a long recording. You'd have to just keep writing down the numbers over time if you want to see how it's changing over time or something like that. But it can give you an instantaneous read of what heart rate is, as well as oxygen saturation of the blood. The ECG, as I mentioned, has these electrode stickers, and if you need someone to go run or do something, you can have them first come in, put the electrode stickers on, measure their heart rate and heart function or electrical activity in their heart, and then you can take the leads off and leave the stickers on because you really want them in the same place. Have them go do whatever they need to do, drink coffee, run around, whatever it is that needs to happen, the variable of interest, and then you can remeasure them again. So they don't have to be attached all the time, but you do have to put these stickers on, which sometimes includes taking off clothing on your socks or tights or something to get at a point on your leg. The electrode stickers are non-reusable, and so that is, it's using more resources and more expensive. We have a lot of them already, so it shouldn't be too much of an issue. Another advantage of the ECG is that if you're interested in the electrical activity of the heart and the functioning of the heart, you get more than just heart rate. So you can look at different parts of the heartbeat rather than just heart rate. So those are different options. All of them have their pluses and minuses. Another aspect of cardiovascular functioning that people are often interested in is blood pressure. So we can measure blood pressure. The equipment that we have now is, we used to use different equipment, but what we've moved to is using this electronic or automatic blood pressure measuring device, sphygmomanometer as they're called, and it does it more automatically for you. So you just put the black armband around the arm, press start, and then it does the rest for you. So it's a little easier to use. The manual ones using the stethoscope and everything was really tricky to use. That's not to say that it's perfectly accurate. So even this automatic one is easier to use. Measuring blood pressure is tricky to get it a good reading and an accurate reading. So sometimes it is a little bit of a variable measurement that can be trickier to find a really strong signal because it's hard to get really good accurate measurements, but using this automatic one device is easier than the way we used to do it, and it will give you the systolic and diastolic pressure. So if you're not familiar with what those mean, the way this works is that the cuff on the blood pressure monitor fills up with air and squeezes your arm, and it measures the amount of pressure that it's putting on you. And you're basically measuring the amount of pressure it takes to stop the blood flow going through your arm and that major artery. So first you go past the point, a high enough point where there's no blood flowing, and then it slowly lets out the air. And at some point, there's enough, the pressure in the cuff is just low enough to let blood start pulsing through. And that point where it shifts is the systolic pressure. So the systolic pressure is when the heart is squeezing, it's the higher pressure. And basically the squeezing of the heart has a high enough pressure to balance or overcome the amount of pressure in the cuff to push some blood through. So it's kind of like a blip. So it's like blop, blop, blop. If you actually listen to the sounds using a stethoscope, the sound that it makes, some people describe it as kind of a knocking sound of the blips of blood making it through your arm are called Korotikoff sounds. When you first hear those Korotikoff sounds, that's the systolic pressure. And then eventually the Korotikoff sounds disappear because now the pressure is low enough to be the same pressure as like when the heart is relaxed, which is the diastolic pressure. So that's where kind of the lowest pressure in the system. And so now things are flowing freely at the kind of rest point. So that's the diastolic pressure. Another piece of equipment we have, this also hooks up to the power lab that we used in lab 1, is where you can squeeze this metal bar that you see here, and that measures the amount of force in that squeeze. So you can measure the amount of grip force. You can measure things like maximum grip force, total grip force. You can get measurements about muscle fatigue and various other things. And so this can help us understand muscle function and how that responds to different environmental variables, like temperature or activation of the sympathetic nervous system through fear or exercise or something like that, or something calming. So we can measure grip force using the grip force transducer. We can also measure reaction time with the reaction time button. It's just simply like a button that you press. So there may be a visual cue, a sound cue, or some kind of distraction or something that you're reacting to, and seeing how quickly you can react. So we can measure reaction time, which is something that's kind of a variable people are interested in looking at, the effect on attention or, how quickly you can react to things. So those are some, I forgot to put on here the respiration belt. We can also measure respiration. It's just a belt that kind of Velcros around your waist and just measures when you expand, when you're breathing in, and then relaxing, breathing out. So you can measure the frequency of breathing. So that's another a device that we have. So we can measure respiration rate as well. Here are some other supplies that we have. We have some things for the calming aspects. So we have some yoga mats, some eye masks, some headphones and things that you can use for, the headphones can be used for if you're doing some kind of guided meditation or sound or anything. They are not noise canceling fancy headphones, but they are headphones that have the earpieces that kind of fit over your ears. They're not earbuds that fit into your ears. You're welcome to bring your own headphones, but make sure that you wipe down the headphones in between subjects. We do have little alcohol wipes that we can wash them off in between people. We don't want to be infecting each other's ears. So we need to make sure to be careful about that. We have some items that can be used for different exercise. We have a few weights in the room, like hand weights, just I think some really little ones and maybe some, I think there's a couple 8 pounds, but we can look in lab and see which ones we have. We have, as I said, a few yoga mats. There are various things you can drink that we can buy if we don't already have. We have some things from the past, like some, instant regular coffee, some instant decaf coffee, we have some tea and some various other things around, and other things that are needed, like cups and spoons for mixing and measuring cups and things like that. If you're doing anything that requires consuming a drink or something like that, make sure that you let us know what supplies you need, how many cups you need, how much of whatever substance it is, whether it's tea or coffee or whatever. Any kind of consumable thing, you need to tell us how much of it you need so we can make sure you have enough. If you're choosing caffeine, there's a link that I can give you, or maybe is on Moodle, that shows some options for caffeine sources that you can use if you're interested in that. And again, we would need amounts of precisely what you want and the amounts you would need for the number of subjects. There's some additional predictor variables that may help you understand your when you're analyzing your data and understanding any patterns you see. It might be useful to collect some of this information from your subjects, like how often they exercise, what kind of exercise they do, their diet, are they, vegetarian, do they eat regular meals, are they, gluten-free or whatever. There may be different diets that could affect things or you're interested in. You can ask about sleep, how much sleep people are normally getting, how much they got the night before they were measured. You can ask about amount of or kinds of caffeine. Are they getting in coffee or soda or whatever? Are they a smoker or non-smoker? How much they're smoking? But there are also things we are not allowed to ask in this particular project. So you're not allowed to ask your participants about their drug or alcohol consumption habits. We're not allowed to ask about any confidential medical history. We're not allowed to ask about sexual preferences or experiences or trauma or abuse. So there are some things that are just too personal and too difficult kind of to deal with in the confines of a course. And we are staying away from all of those kinds of things. By the time you begin your collection of data for your projects, you need to have completed the CITI training on how to work with human subjects. And we need to be very careful to ethically treat our human subjects. So confidentiality must be assured. Participant data and survey answers must be coded in some fashion so that participants' identity cannot be identified. So we need to make them more anonymous so that we can't figure out who is who after the data is collected. You must provide informed consent or receive informed consent. So you must inform your subjects and then they must consent to the project. So they must be informed enough so they know what's going to happen. So the participants have to be recruited in a particular way. We are allowed to recruit outside of the course, but they must be Smith students, and you must recruit them either through an email or something written. You can't just say like, hey, so-and-so, be in my subject, be a subject in my project. You would need to actually also, you can ask them, but you should also send them an email so that they have a written record of being recruited, and you should have enough information in there. And we'll give you a standardized kind of blurb to adjust to your project that should be used with all of your recruited participants. All participants have the right to refuse for any reason. You cannot force anyone to participate. And it's really important that choosing not to participate doesn't affect your relationship with the participant, other people, other peers, or the course instructor. So if someone says they can't participate, that's it, they're done. They don't need to participate, and that's fine. We should make sure to minimize risks to participants so they can't participate in a project where you're looking at, increased heart rate or something if they have cardiovascular or respiratory conditions that could be triggered in the study. So we need to make sure that everybody's safe and isn't doing something that they shouldn't be doing. And sometimes something happens that is unexpected. So experimenters must always be monitoring participants' health during the experiment and make sure that, For example, sometimes the blood pressure cuff can be really quite tight and can bother people, and if you're doing repeated measurements can really cause some problems. So you need to make sure that you're really paying attention to your subjects and that you're not harming them in any way. Vulnerable populations may not participate, including people under the age of 18, pregnant people, or people with physical or mental disabilities. So vulnerable populations are not allowed to participate. So part of the pre-lab for this lab also includes a video talking about experimental design. So if you haven't already looked at that, make sure that you watch that video as well. It talks about some of the aspects of how to design a good study. But for this particular experiment, you will need to, in lab this coming week, you will need to explain what your project is in quite a bit of detail. So the first thing you need to do is tell us what is your hypothesis. Now, there's a lot of confusion, even amongst practicing scientists. What is the definition of hypothesis and what it actually is? So there's also some reading for you to do on what a hypothesis is and how it's different from a prediction. So a lot of times people conflate the two and think that a hypothesis and prediction are the same thing. They are not the same thing, technically speaking. And we want to make sure in this class that you understand what a true hypothesis is and that it is not just the same thing as a prediction. So one definition, a common definition of what a hypothesis is actually an explanation or generalization on trial. So you're basically saying, this is what I think is going to happen and why I think it's going to happen. This is the explanation. This is the pattern that I expect to see. And then you test to see if that's really true. So that's the on trial part. So you're basically saying, like, this is what I think is going to be, this is what I think is going on. And then it's on trial because you're going to actually test it, right? So a generalizing hypothesis is basically a description of a pattern, and an explanatory hypothesis is a possible explanation. And we are going to be focusing more on explanatory hypotheses in this class. So you should be giving us some possible explanation. The prediction is more specific on what you expect to see in the results. So the prediction is like, if I'm right, if my explanation is right, then my prediction is that I should see this when I get my results. Okay, so the hypothesis is the explanation that you're seeing if that's really true or not, and the prediction is what you expect to see in the results. And it can be tricky. Students seem to, everybody, not just students, because a lot of practicing scientists get this wrong too, but a lot of people tend to think that prediction and hypothesis are the same thing. So after doing the reading and after thinking about it and trying to write your own hypothesis, if you're still confused about how to write a good hypothesis, please feel free to ask for some feedback and help on that. Once you've decided the overall question that you're interested in and you've developed the hypothesis, which again is the thing that you think is going to explain what you will see, and then the predictions, of course, are what you expect to see. The hypothesis is the explanation that would explain why you got those results. You have to explain how you're going to do an experiment to test all of this, right? So you need to say, what treatment groups will you compare? So these would be your independent variables. And again, if you haven't watched the video on variables, make sure you do that so you're clear on what an independent and dependent variable is. So the treatment groups are your independent variables. So those are the things that you want to see. Does this have an effect? Does caffeine versus decaf have an effect? Does exercise versus this kind of exercise versus this other kind of exercise, or cold versus hot, or meditation versus nothing, or whatever. So it's the thing that you're trying to see. Does this have an effect? And that question I asked before, what is the effect of blank on blank? It's the first blank, okay? And then the thing that we need to know what you're going to actually measure, that's your dependent variable. So that's the last blank. So those are the things like heart rate or blood pressure or grip strength or respiration rate or whatever. So those are the things that you're going to actually measure. And then you also need to tell us how you're going to measure this. So like, what is the process and what supplies you will need. So we need to know which equipment you want to use, if you need consumable supplies that only get used once and get thrown away, like electrode stickers or cups for drinks, or anything that's going to get used up and we need to make sure you have enough of. You need to give us exact amounts. We expect to have this many subjects, so we will need this many cups or this amount of coffee or whatever. You should make a visual representation of your experimental protocol. So a flow chart being kind of like, what groups do you have? If you're in this group, you do this. If you're in this group, you do this. What is the time course? What are you doing at the different time points? Where are there resting points? Are you measuring more than once on the same person? Are you measuring only on different people? So making a flow chart that actually describes how you're doing the experiment. And also, what is your sample size goal? So how many people, how many subjects are you going to aim for? And please note that the more people, the better. 5 subjects within each treatment group was really a minimum. I mean, the absolute minimum is 3, but 3 is really ridiculously small. Even 5 is on the too small side. So you want to aim for a real minimum of 5, but you're looking the more people you can get. So it'd be better to do 10 people in each treatment, or 12 people, or 15 people. Now, it can be challenging to get enough people, but you should aim for getting as many people as you possibly can fit. We have 2 lab periods devoted to collecting data, but you're also welcome to come outside of lab time if you wish to. So if you want to get even bigger sample sizes than you could fit into 2 lab periods, you're welcome to come outside of lab time. You will have better results, stronger results, better evidence if you have a bigger sample size. You also really need to think about how you will control for things that you're not interested in to reduce bias. So order of treatments, or make sure you're picking people that are similar to each other in everything except for the one thing of interest. So you wouldn't want to pick all athletes in one treatment and all non-athletes in another treatment if that's not the variable of interest, right? So if you are comparing the effect of caffeine on heart rate, you wouldn't want to pick all athletes in the caffeine group and all non-athletes in the non-caffeine group. So you need to make sure that other variables aren't confounding the one that you're interested in. So you want to make sure to control for other things. You don't want, in some cases, things like blood pressure can change over the course of the day. So you wouldn't want to measure some people in the morning and some people in the afternoon. You'd want to be consistent about time of day and control for as many things as possible. So if you don't want smoking to be a factor, maybe use all non-smokers or whatever. So you need to make sure that you're reducing bias and kind of keeping things as even as possible and as controlled as possible in all variables except for the one of interest, which again you're controlling by having some people in one category and other people in another category, or measuring the same people in 2 different conditions. The final thing you will need to do in your experimental design is explain what you think your results will look like if you get what you predicted, if your hypothesis is actually supported. So you will need to know what type of graph is best to use and what that graph will actually look like. And certainly we're more than happy to help you figure this out if you're having trouble, but think about if your hypothesis is supported and your explanation is supported, then what would you predict to see in your results? What data, what treatments would be higher than the other or different from the other? How may time course matter or whatever? So make sure you're actually thinking about what you expect to see in your results. And that gives you an overview of the kinds of things you can do and the kinds of things you should think about and how to put together your experimental design in class in the second week of lab.